Hello, good morning to everyone. I have two presentations now. In the first one, I will try to present briefly the summary of the working package number 1 that we've been dealing in the last 3 or 4 years. It is strictly related to susceptibility of arches to degradation under service loading conditions. Moreover, what we really try to do is try to select the structural types that are more sensible to develop this kind of damage under normal loading. And this was the main reason for this. It was we are having quite a lot of problems. We are having damages, we are having defects, and not only durable defects. I mean defects that are due to strength mechanisms on the arch. And on the other hand, if you perform ultimate limit state analysis, you are getting very good results. No? So on the one hand, you do ultimate limit state analysis and you have partial coefficients of about 3, 4, but on the other hand, you go to the site and you can see damages, you can see defects. No? So we were trying to explain this apparent paradox, no? And this is quite an important thing, because I think is after 30 years, I think we have a knowledge of how this bridge collapsed, no? More or less we know all the collapse mode. We have developed very good tools as RGM or Ring to perform ultimate limit analysis, but maybe this is not the main key to manage these bridges. No? There is something more, as Matthew has already said, about permissible limit state. So what we try to do is we go back to the very beginning. We wanted to study which are the real loading conditions that we have on the bridge. No? It's not only the axle load, it's the separation of axles, the real trains that we have in our lines. And then we also try to study specifically which are the bridges that normally, if you see, well, we have quite a lot of information because of the catalog, no, that we developed in the previous stage. So we found damages or defects in all kinds of bridges, but some of them were specifically related to certain typologies, to certain spans and ratios and the slenderness. So in the second step, we did some parametric studies, specifically leading with this geometrical ratios. So the first thing is all of us, we know that all the live loads have evolved a lot during the last 100 years. No? So these bridges were designed and built for a completely different exploitation condition. Of course, they are survivors. They have been there for 150 years. But we have to be aware that real loads have changed a lot, and code loads have also changed a lot. No? This is an example of the Spanish code. We didn't have any codes before the 20th century. There were more special prescriptions for lines. No? They were private lines, like here and in France. But starting the new century, the 20th century, we started to have some kind of a general codes issued by the government. This is a Spanish case, but the French and the Italian are very, very similar. So this is the axle load that we have. Now we double it. No? It's 2 times, which is quite representative. If we look at the total live load of the total weight of the locomotive, it was about 450. Now it's 1,200. Again, it's more than double. So we have to bear this in mind. And what about the impact coefficient evolution in the codes is quite funny, because the evolution is completely weird. No? This is what we have now. That is very over-conservative for very low spans. And this is more or less what we have had during the last 100 years. It changed a lot. No? So the second thing that we did is try to think whether or not the UIC load patterns are the worst thing that can happen in our bridge. Because they were not think at all for our bridges, I tell you. So maybe if you go to UIC and you get this 4-axle load, you think it's the worst thing that you can happen. Is not the worst thing for sure. So we have to rethink which which load patterns we think can be the worst situation for our bridges. And we ended with these three: the maximal load, the maximal load over the bridge, the maximal axle load, the maximum load over the bridge, and the maximum difference between one half and the other one, no? And then we have a look of all of the trains, well, not all, but a lot of the trains that we all have in Europe, no? Paying special attention to passengers, freight, and exceptional convoys. We were looking to this kind of a span, 5, 10, 15, and 20, and it was a very, very easy analysis. You only get the span, and you were trying to get how many axles that you have in one half on the other one. It was only a geometrical analysis, no matter which is below the track, no? It's very, very simple. So, this is more or less what you have. You know, we have type 1, type 3, type 5 in Eurocodes, and then we have real trains passing over. No? So this is more or less what we have, looking at these trains, taking into account these spans. No? I think here we have, well, we did it for passengers and also for freight. This table is quite useful because we normally think that masonry bridges are very massive, no, not like steel bridges. But if you go to this kind of a span, 5, 10, for example, if you compare the maximum load to the total weight, is even 66%, which is quite a lot. So it's really make a difference when you have a train over the bridge. Of course, if you go to 20 meters span, these relations are lower. But be careful with these spans because they are more sensible to live loads, of course, than the big bridges. So we normally have these problems here. And this is another thing, we compare passengers with freight trains in order to relate it to the importance of the impact coefficient. Again, it's a playing with the axles and the spans, so sometimes we only have 2% difference, sometimes we have 20% difference between the freight and the passengers. And here more or less is the same. So all of this work is gathered and described in one of the background documents. No? There you will see all the trains that we really have and the difference between the countries. We do not have, well, we try to have similar axle loads, but we don't have exactly the same one. And the other thing that is quite important is we do not have the same distribution of axles, no? Which is another thing that can matter a lot in these bridges. So apart from this very, very simple geometrical analysis, we try to analyze also if what is below the track has some importance in this selection of the trains. No? Of course, the shape of the barrel, the thickness of the barrel are very important in the structural behavior, but after performing some ultimate limit analysis with ring, they have more or less the same importance in all the trains. So the previous selection that we did, it was already assumed. So then we focus on short spans and, well, medium spans with this slenderness and with this rise to span ratio and with this hunching, because we have detected that most of the problems that we have are related with cracking and things like that were located in these structural types, in these geometries, in these ratios. No? So we were, as I was telling at the beginning of the presentation, we were trying to explain this paradox of why we have good ultimate limit state, but we still have problems. We were searching someone to blame, no? Maybe the stresses, maybe local problems, because it is difficult to explain to the client that if you do the numbers, you have 3, 4, but then you go to on site and you are full of problems. No? So to tell you the truth, to be honest, we didn't know what we were searching for. Also, we thought we could have some problems with stresses locally, but we also thought that the real problem is that when you increase the live loads, maybe the barrel can support the new thrust, but it's going to give a huge horizontal action to the abutments. If the abutment is not well supported by the passive pressure, it's going to overturn, and if you have the overturning, you have a 3-hinge mechanism in the bolt, and you have this every time a train passes to the beach, you are having this many times a day, no? And this is related again with fatigue problems and the permissible limit state. So what we did also is play with different models, with different height for the abutments, and well, we were searching also for certain local problems. So the second stage, once we more or less select which were the real trains that we were going to analyze, and once that we have select more or less the cases, the geometry of the bridges that we wanted to analyze, we started to do a lot of numbers, no? So this is more or less the parametric study that we did. 4-meter span, race span ratio, the depth of the field over the crown, the backing, the lengthiness. So we did quite a lot. The problem of doing such amount of numbers is that you can lose the sense of reality. You can even lose your head, no? Because at the end you have many numbers and you have to correlate them, so it's quite difficult. Especially when you don't know what are you searching for, no? That's another thing. So we established in the models, we did some 2D models and 3D models. We established some masonry section controls in order to compare between one case and another one. Reaction, of course, stresses on the infill, vertical and horizontal, crown and rigid. Also, we established this vertical section in order to know more or less which are the the earth pressure that we were mobilizing in that sense. We did a model very similar to the one in Dublin, to the NEAM one, but we used more Coulomb instead of Drucker-Prager. Well, it's numbers, so I don't think it has a lot of importance. We use Plaxis for 2D, and we use Sophistic, which is a general program for 3D models. Well, at the beginning, we were only playing with geometry. All of the parametric studies were focused on geometry. So we used the same properties for all of the models: dry weight, jump modulus, Poisson coefficient, cohesion, internal friction, well, dilatancy, tension cutoff. So we start with these very simple models with the trains that we have selected, no? We did two. I know Plaxis is more a geotechnical program more than a structural one, so we double check with Sophistic. This is Plaxis, this is Sophistic. We more or less have the same results. So maybe both of them are wrong, but both of them gave us the same results. No, it is funny because we call these bridges structures, but sometimes the behavior is more related with the geotechnical work. So we are always talking about the barrel, the abutment, but the infill is really important, as we will see. Well, this is more or less the properties that we get for the backfill and the granular infill. And then we start to compare stresses all over the bridge. And it is true that all of the results were very predictable. I mean, were in the sense of the normal behavior of arches. We couldn't blame the stresses. There is no way that with normal analysis, with this property, with real trains and with real geometries, we could have problems with stresses in a masonry arch bridge if this model is all right, because normally we are about 0.6 megapascal, 0.8, 1 megapascal, which is not a lot for peak stresses, not for mean average stresses in the section. So it's quite difficult if all of the elements are healthy. I mean, the infill is well compacted, the masonry is all right, to blame the stresses or the strength problems in the masonry arch. No? We did quite a lot of this. Is different rise to span ratio, and this is the stress that you have in the peak stress for a 6-meter span. Well, all of this again is in the background documents. Here I have bring some of the some of the values. We have very little cracking also for this ratio of slenderness. So for normal traffic with well-compacted infill, with good masonry, not a lot of cracking is expected, 5%, 6% of the section. So, and remember, these are 2D models. We will go on the strip or the width, effective width that we took into account, but there is no expanders here, okay? So it's over-conservative analysis. And if you move to the infill pressure, they are nonsense. I mean, they are very, very little. You cannot explain a bulging of the spandrel due to the horizontal pressure that you have in the infill due to this analysis. Here again, this is more or less what we have on the one side. Of course, if you have a very shallow arch, you're going to have less horizontal effort. Here you can see these are the different values for passengers, freights, wherever. So again, all the results were quite predictable, but the amount of, here we have about 400, 500 kilonewtons for 2.5 meters of width. So it's not a lot, again, of the horizontal reaction for an abutment or for a pier. And so, to be honest, we were not very successful with this analysis. We could not blame our first variable. What we did is what happened if we change the backfill properties. No? We did, again, the same parametric study, but varying the backfill and the infill properties of the bridge. And it's quite funny because well, first of all, let me show you one comparison. For example, if this is a service analysis of a bridge, and the maximum stress that we have in the springing is 1.6 megapascal. If you do a ring analysis with the same values, you have a failure load factor, a safety factor of 4.76. No? So this is related to what Matthew has said, is ultimate limit state and permissible limit state related. Can we relate this to this in order to fix which are the safety factors for service loading? It's quite difficult. So we move and we start to change the properties of the infill, especially the modulus of elasticity, the Young's modulus. It doesn't have a lot of sense in terms of infill, but it's the way where we can control this parameter in the analysis. So again, we start doing a lot of numbers. And in this case, if you change the infill properties, the mean stress of the section does not change a lot, but the peak stress in certain section can change a lot, okay? So we did the same analysis. If you go to the springing sections, if you change a lot this value in relation to the stiffness of the bolt, you will have bigger peak stress, about double or even triple the value that you already have, no? And again, this is related with ultimate limit state and this kind of service analysis, no? Because we found that if you change parameters of the infill, you are not going to have a lot of changes in the ultimate limit state analysis, but you will have quite a lot of changes in the stresses, no? So apparently there are some variables that do not have a lot of incidence in the ultimate limit state, but can have an important incidence under normal loading in terms of stresses and in terms of distribution of loading, no? This is more or less what I am telling you now. Normally, in the overall of the bridge, not a lot of changes are expected, but in some of the conditioning sections, you could have great changes if you play with this variable. And what we did, we could blame a little bit to the infill, but we were not very sure if it was guilty for everything, no? So what we did is trying to model the surroundings of the bridge as well. This very colorful presentation is always a lie, no? Because you can do whatever you want here, no? But it is true again that if you have geotechnical strata that there is not very well compacted or can be washed, you are going to have some movements. So this is try to study this issue more in a geotechnical way than in a structural way. So again, the complete models always give you an increase on certain variables, not to the mean stress, because there is depending only of the point of application of the force, no? But you can have changes in the peak stress, which is what we were looking at. Well, again, more numbers. We did some 3D models. Okay, we use Sophistic for this issue. We get 8 meters span and 12 meters span. We didn't repeat everything, but we were focusing on these 2 cases. We established again some longitudinal control sections and also some transversal section, and we play again with a double track bridge with these situations. So these are the longitudinal section. We were looking again for stresses in the crown, the springings. In this case, we could analyze in some way the transversal behavior with a loaded track, only one. And again, we started looking for stresses, mean average stresses, peak stresses. Of course, in all of the cases, we have a reduced stress because we have a role. We have the spandrels play a role not only as the stiffeners of the bridge, but also as elements that carry thrust. Okay? So what we did, main conclusion of the analysis, model performed similar no matter the program. Stress distribution obtained both masonry and infill was as expected, was predictable. For all the convoys, real trains that we analyzed, very little cracking was expected and not very high values for mean and peak stress, over 1 megapascal. And the horizontal stresses in both directions obtained in the field were very small. So we really found that maybe the stiffness of the granular infill can play a role in this service loading if they are not very well compacted. But at the end of the morning, I will show you an example of how to retrofit a bridge injecting the infills. The span, of course, have a big influence because of 2 reasons. Firstly, because greater span leads to greater value for the stress, of course, and also in relation with the load patterns that we have in real trains. So sometimes 6-8 meters span can be more sensible to real trains than 20 meters span. The peak stress increased greatly in the cases in which a medium-low characteristic granular infill exists with a high deformity compared with the bolt. So that's what we were talking about. We have to take care about which is the structural meaning of the infill and which is the real role that he is playing in the overall mechanism. And of course, if you model everything and you allow too little movements on the foundations, you will have different stress distribution. But it is true that in order to be representative, you have to have very low geotechnical properties strata in the surroundings. Normal things do not affect a lot. Well, this is again more or less. This is something that I think this is important. There are some variables and some properties that maybe do not affect a lot in the post-critic mechanism of ultimate limited states of our bridges, but they can affect quite a lot in the normal life of these bridges. And I think the infill properties is one of these. So we have done with Ring software, we have tested the importance of changing some of the properties of the granular infill, and in ultimate limited state, it does not have a lot of importance, and I think it's true. I mean, it's not a problem of the program. It's a problem of the mechanism that you mobilize in ultimate limited state. But in service analysis, I think this is quite important. And of course, if you do 3 analyses and you are looking for defects, you can look and you can model or other type of defects that you cannot do in a 2D analysis, of course. And this is true, especially the crack in the ball, not the transversal one, the longitudinal one. You have to be very, very careful. But if you are going for a 3D analysis, you have to have a lot of data. No? That's the other point that Niam told us yesterday. No, it's not fair to do very complicated models if the data is not reliable. Well, and the main conclusions is we will go on it in the next presentation, but this is important. When are we going to say that we are violating or vulnerable the service limited state or maybe the permissible limited state? No? When are we going to define that damages are or defects are important enough in the breach to do a repair or a restoration of it? No? Is when we change the stiff distribution of the breach, is when the breach finds another load path to carry the load to the foundation. And it is true that this service loading, I don't know how to call it, maybe permissible limited state, serviceability limited state, is often violated long before that ultimate limited state. And that's the problem in masonry bridges, that we can have very, very big values for the ultimate limited state, but we are not accomplishing the permissible limited state. And this distance, as Matthew has already said, it changes a lot depending on the breach, depending on the construction details, depending on if they have internal spandrels, depending of everything. No? And another thing that I think is quite fair to indicate is we normally try to solve everything by numbers, and for these problems I would suggest not using numbers. Okay, for me 3D analysis is not a 3D model, it's a 3D analysis, maybe it's monitoring, maybe it's whatever it has to be. But it's very difficult to catch these problems with numerical analysis because, in my opinion, they are not related with the stresses or whatever that we normally use in our programs. No? You can use Abacus, Sophistic, whatever you want, but the problem is not related with the stresses. The problem is related with compatibility and stiffness in the bridge. So sometimes doing a good monitoring, a very simple monitoring, can give you more information that many of these analyses. And to end, where I should recommend to do this, especially service analysis. So bridges in group 3. Group 3 is, well, I am going to talk about this, is in the assessment of damaged arches. We created a group 3 for special problems. In certain types where geometry are over here, we have found that there can be some problems because of the slenderness and because of the geometry of the arch, of course, for skew or curved bridges. In all of the bridges that we have complex internal stiffness distribution, for example, the presence of internal spandrels, the different types of infill, and of course, every time that you want to increase the axle load, and not only to increase the axle load, to change the distribution of axles in a bridge. No? And that's all. Thank you very much.